Hey guys, Dr. Blister coming with a fantastic chemistry video, and today we're going to talk about primary, secondary, and tertiary carbons and hydrogens. Very simple stuff. First of all, this is CH4. This is not primary, secondary, or tertiary. This is just methane. So if you have anything like that, CH4, you just call it methane. So that's not primary, secondary, or tertiary. It's just methane. What does primary look like? Well, if you have something like this, these are primary carbons. And attached to the primary carbons are primary hydrogens. Okay, so these are both primary carbons. Attached to the primary carbons are primary hydrogens. Now, they're also abbreviated, just so we're all on the same page, they're also sometimes called first degree hydrogens or carbons. Now, how do you tell a primary from something else? Very, very simple. A primary carbon has one other carbon attached to it, and only one other carbon. So notice this carbon here has one other carbon attached to it. Everything else is hydrogen. Therefore, it's primary. Okay? What about secondary? Well, as the name implies, there's two other carbons attached to it. So let's take a molecule like this, like propane, for example. And as you're all probably guessing, carbon here and a carbon here, those are primary carbons. Just like these ones are primary, same idea. So these are primary hydrogens. Oops, not that one. These are primary hydrogens. Now notice, each one of these carbons has one other carbon attached to it. But this one in the center has two other carbons attached to it. This is known as a secondary carbon. And these things are secondary hydrogens. All right, so we have primary carbons, secondary carbons, and now tertiary. Well, if primary is one other carbon attached to your carbon or to the carbon of interest, then secondary is two other carbons attached to it. Then tertiary must be three other carbons attached to it. All right. All right. So these three carbons are all primary because they have one other carbon attached to them. So that means that these three hydrogens are all primary hydrogens. This carbon, however, that is a tertiary carbon. And attached to the tertiary carbon is the tertiary hydrogen. Okay, and this is what we call them: primary, secondary, tertiary. There's also quaternary. Quaternary is not all that interesting. A quaternary carbon has four other carbons attached to it. So this carbon here would be called quaternary, and there's no quaternary hydrogen on a quaternary carbon. That doesn't exist. All right. So there's how you name or how we identify hydrogens and carbons in organic chemistry: primary, secondary, and tertiary carbons. Attached to those carbons are the primary hydrogens. Hope that made some sense. Now, Let's take a look at these two reactions here. Essentially what we're going to do is we're going to take propane and a little bit of UV light, and we're going to get a mixture of products this time. Okay, so two different potential products. One is reacting at the primary carbon. The other one is reacting at the secondary carbon. Now, if we think about this a little bit, it stands to reason that the methyls should react more. The methyls should react more. Why? Because the first step in the mechanism, if you recall the mechanism of chlorination, the first step in the mechanism after radical formation is the chloride radical, free radical, will abstract a hydrogen from a carbon. That's the first step. So if the first step is hydrogen abstraction, there are 6 hydrogens on the primary carbons. 6 hydrogens. The secondary carbon only has 2. This carbon only has 2 hydrogens. So just by pure gambling odds, the collisions should occur more often at the primary carbons, not the secondary carbon, because there's only 2 of them, right? So let's take a look at the results. It turns out that the predominant product in solution, or in this reaction, is the secondary chloride. So that's with the chlorine on the middle carbon, the secondary carbon. We didn't get as much, or we didn't get a predominant yield of this one, which you probably would have thought initially that's where it should have been. It should have been the methyl group that lost its hydrogen, and then it attached the chlorine to the primary carbon. But it didn't. The majority of the product is this one, where the chlorine is on the middle carbon. So that kind of flies in the face of my idea of, well, it's just gambling odds, right? There's more hydrogens on the methyls, therefore there's more collisions, therefore there's more reactions. Turns out that's not the only thing you have to consider. Collisions, energy, orientation. So collisions is only one part of it. The energy is the other. So it must be, because these hydrogens came off easier, or I should say faster, they must be easier or take less energy to abstract than the methyl ones. It must be that way. Now, all right, so let's take a look at the mechanism of this reaction. Now, whenever you're doing stuff like this, it's important to understand that you have to draw the mechanism in order to explain what's happening in the flask. So the first step of this mechanism is radical formation. There we go. Now, after we make the radical, then we react it with our propane. And we form this radical. And that radical will continue on, react with chlorine. To give us the product. There we go. So there's the chlorinated product. Next, we have to explain the other product, the product with the chlorine on the secondary carbon. So we're going to do the same mechanism. We're just going to attack a different hydrogen. And I know what you're thinking, Dr. Betts, do I really have to draw the mechanism twice? Yes. Yes, you do. Don't be lazy. Okay, and so there's our mechanisms. Now, I'm going to give you a big hint. The answer in this class is I shouldn't say always. It's almost always the reactive intermediate. These radicals are reactive intermediates. There's also carbocations and carbanions we're going to talk about later on, but these two things are reactive intermediates. And the key to understanding organic chemistry is understanding that the reactive intermediate that is the most stable, that is to say, the least reactive, that is to say, the easier one to form, that is to say, the one that has the least energy required to form, that is to say, has the lowest activation energy, will form faster. So imagine we have the potential to form this reactive intermediate and this reactive intermediate. Let's say, for argument's sake, that A never forms. It just too high energy, won't form. Let's just argue that. It does form, but let's just say it doesn't for argument's sake. Won't form. So no matter how slow B forms, the only product you're going to get is from B because it's the only one that's forming. Okay? Now what's really happening in this flask is A will form a lot slower than B. B will form a tremendous amount faster. So because B can form faster, it will accumulate more and it will react more because there's simply more of it to react with. Okay? So because B has a lower activation energy to get to the reactive intermediate, it will form faster. And because it's forming faster, it will react more to give you product, which is why the yield will increase of this product versus this one. Okay? Because this intermediate forms faster, this is the more abundant product. This intermediate forms slower, so this is the minor product of the reaction. And that's how organic chemistry works. The reactive intermediates that form fastest will dictate the outcome of a reaction. If there's reactive intermediates, not every reaction has them, so keep that in mind. So let's look at the stability of free radicals. It turns out that tertiary radicals are the most stable. They will form the fastest in a chemical reaction. Tertiary radicals are the most stable. They'll form the fastest. The next most stable, secondary. Secondary is the next most stable. So tertiary is the most stable. Secondary is the second most stable. Primary is the third most stable. And the least stable of them all is the methyl radical. It's just a horrible radical, not very stable at all. So of the four of these, this one will form the fastest. This one will form the slowest. So if you had a reaction in which this radical or this radical had the potential for forming, this one is going to form much faster because it's much more stable. Okay? And that's how it works. The radical or the reactive intermediate doesn't have to be a radical. The reactive intermediate that forms, that is the most stable, i.e. has the lowest potential energy, will have the lowest activation energy to get there. It will be the one that forms the fastest and dictate the outcome of the reaction. So now let's take a closer look. Take a look over here. There's my secondary radical. There's my primary radical. Now take a glance right in here. Take a look right in here. The green line is the secondary radical formation. The blue line is the primary radical formation. It's really important that you look at this. The blue line is higher in energy. Energy goes up as you go higher. The blue line is higher in energy than the green line. And this difference in activation energies is enough to dictate this reactive intermediate will form faster because it takes less energy. Remember, it's collisions, energy, orientation. This one, the molecules don't have to be going as fast. They don't have to be colliding as hard. So it's going to form faster because it's going to have more effective collisions. This one will form slower because it's going to have fewer effective collisions because it's not going to be slamming together fast enough. So this radical intermediate, this reactive intermediate, will dictate the majority of the product. Doesn't mean this one won't form. It certainly does. But this one forms preferentially, and it's going to form the major product. Now, at this point, I'm going to just stop this video. We're going to come back and talk about reactive intermediates in the next one because this is a pretty big topic that's very important for you to understand, and this video is already getting a little bit long. So right now I want to wish you all good luck and good chemistry. I'll see you in the next video.